So I hope everybody is very much interested and excited to learn the tensors. So we'll start with tensor analysis. So before going to the tensor, I think we should build the basics from the fundamentals. So slowly we'll start with scalar. So what is a scalar? A scalar or an invariant quantity does not change under a coordinate transformation, right? For example, consider a coordinate transformation x mu to x prime mu. Okay, so x mu, here mu is an index. Okay, mu is an index, and mu can take the values 0, 1, 2, 3, etc. up to n, where n is the dimension. In 4 dimension, mu can take 0, 1, 2 and 3. This is in 4 dimension. Okay. So consider the transformation x mu to x prime mu. So x mu is one coordinate system and x prime mu is the transformed coordinate system. After the transformation, this is the coordinate system. So I will represent it by prime. So this is transformed coordinate system. So scalar quantity is a quantity which is invariant under a coordinate transformation. So this is the old coordinate and this is the new coordinate system. And scalar quantity is such a quantity that does not change under coordinate transformation. For example, consider f phi. Okay, phi is a function and let phi depend upon the coordinate x mu. Okay. So phi is a function in the old coordinate system, that is the unprimed coordinate system, and it is said to be invariant if it remains unchanged under the transformation. Okay, so x mu is transformed to x prime mu. Then what will happen? Phi of x mu will be transformed to phi prime of x prime mu, right? Or in other words, I can write f of x mu is equal to f in the sense phi. Okay, phi of, now the transformation is given by x mu going to x prime mu, which means x mu is a function of x prime mu and vice versa, because you can transform from one coordinate system to the other coordinate system and back also. So there is a relation between x mu and x prime mu, so you can write x mu as a function of x prime mu. Okay, therefore phi of x mu can be written as phi of x mu, where x mu is the function of x prime mu, right? So when you do the transformation, you will get phi prime of x prime mu. So you get phi of x mu is equal to phi prime of x prime mu, which means that phi of x mu and phi prime of x prime mu are invariant, or they are the same. But when you look at this form, it might look as if different. This is phi and phi prime. So this form is different, but the values are equal. Form is different because one is phi and another one is phi prime. Therefore, the form might be different in some cases, but the value will be equal, or the value remains the same. So such quantities are called scalar quantities, and they are reducible to each other by a coordinate transformation. The form of the function may change, but its value does not. For example, the physical quantities like mass, energy, volume, temperature, density. Density in the sense mass density, mass by volume, right? So all these are scalar quantities. So scalar quantities can be described by one number, and this number does not depend on the coordinate system. It is invariant. Similarly, we know vectors. So next we have vectors. The concept of vector is very much familiar to all of us, right? And in usually in pre-relativistic physics, when relativity was not invented, in the pre-relativistic physics, it is assumed that space has a natural structure of three dimension, right? A three-dimensional vector space with rules for adding and multiplication. For example, the triangular law of vector addition, the parallelogram law of vector addition. So the vectors follow a certain rules for addition as well as multiplication, the dot product and the cross product. But once the special theory of relativity came into picture, then spacetime had a natural structure of four-dimensional vector. So you usually represent it as x mu equal to ct, then x naught, x1, x2, x3. But in general, we can represent as n dimension. Okay, so n numbers. Vectors can take n numbers in n dimension. N numbers in the sense these are the components of the vector. So vectors can take n components in n dimension. Now in a flat space, you can represent the vector by a line segment. So usually we represent like with the line segment with an arrow, right? So for example, let this be vector A. Then let this be another vector B. So how do you add two vectors A plus B? Then you have to connect these two, right? Then you put an arrow here. So and let this be C. So A plus B equal to C. But this is in a flat space or a Minkowski space. But what will happen to the definition of vectors when you consider a non-Euclidean space or a curved space-time or a Riemannian space-time? Then you cannot define the vectors in the same way as we have done so far, right? In a curved space-time, this vector space structure is lost. We'll see how it is. Because whatever is a straight line in the flat space, when it goes to the Riemannian space-time, I'll represent it by RST. This is the Riemannian space-time. Then it will be curved, right? So if you have a triangle in flat space or in the Euclidean space, then in the Riemannian space-time, you will get a curved triangle, something like this, right? It will be curved. So here the angle, the sum of the angles will be 180 degree in flat space. But in Riemannian space-time, the sum of the angles not equal to 180 degree. So if you add all these angles, it will not be equal to 180 degree. So depending upon the curvature, if it is negatively curved, it will be less than 180 degree. If it is positively curved, then it will be more than 180 degree. So what is the general definition for vector? So you cannot define vector in flat space in a different way and in curved space in a different way. So you need a common definition for vectors for both in flat and curved space time, right? So in general, the vector can be recovered in the limit of infinitesimal displacement about a point. For example, consider a function f of x alpha. Okay, here x alpha is a coordinate and f is a function of x alpha. Let this be a function. Okay, now I have to define this function in a curve. For example, any curve, you can imagine any curve, and I will represent this curve by x alpha of sigma. Here sigma is a curvature parameter. Okay, so this will be sigma is a curvature parameter, and I will define this curve as x alpha of sigma. So I have a function f of x alpha and I have a curve x alpha of sigma. Now the directional derivative along the curve. So at any point in the curve, you can define the directional derivative, right? That is defined by df by d sigma. And I can write mathematically as limit of epsilon tending to 0 f of x alpha sigma plus epsilon minus f of x alpha of sigma divided by epsilon. This is the general description of the directional derivative. Okay, so we can write the directional derivative as dx alpha by dx sigma and partial derivative of f with respect to x alpha. This is because f is a function of x alpha. So here you can see f is a function of x alpha, but x alpha is in turn a function of sigma, right? So direct, I cannot take the derivative. How do I take the derivative? Derivative with respect to the partial derivative with respect to x alpha and the complete derivative of x alpha with respect to x sigma. So this is how I have to take the derivative. So df by d sigma can be written in this form. Now here sigma is the curvature parameter. That is, as sigma changes, the curve changes. So since sigma is a curvature parameter and as sigma changes, the curve also changes, this quantity dx alpha by, sorry, this is not dx sigma, this is d sigma. D sigma. This quantity can be written as, I'm just denoting it as d alpha. Okay. And this quantity is called the tangent of the curve. Here you can see, so I'll just repeat it once again. So you have a function f which is a function of x alpha and a curve which is defined as x alpha of sigma, x alpha which is a function of sigma. So the directional derivative df by d sigma can be written as the total derivative of x alpha with respect to sigma, because x alpha is a function of sigma, and partial derivative of f with respect to x alpha. Why partial derivative? Because f is a function of x alpha and x alpha is in turn a function of sigma. Therefore, I have to take the partial derivative of f and complete derivative of x alpha. Now, since sigma is a curvature parameter, as sigma changes, the curve changes, and dx alpha by d sigma, this rate of change of x with respect to sigma, can be called as the tangent of the curve. So, this is the definition for the tangent. So what I have done is infinitesimal displacement of this function along this curve, right? This limit epsilon tending to 0 is nothing but the infinitesimal displacement of the function at a point. Therefore, we can say that the tangent gives the infinitesimal displacement at a point. df by d sigma can be written as t alpha partial derivative of f with respect to x alpha. Okay, so this is the directional derivative. Directional derivative. This is the tangent. This is a partial derivative. Now, we are in a pursuit to define vector, right? So, suppose you have a vector A. I can write vector A as its component and multiplied by its basis vector, right? So, A alpha is its component and a basis. This is the general form of a vector. Now compare these two equations. Now if you compare these two equations, you can see that the directional derivative itself will act as a vector, right? So the directional derivative is a vector and the tangent is given by, tangent is the component of that vector, and the partial derivative of f with respect to x alpha is the basis vector. Partial derivative of f with respect to x alpha will give the basis vector. So the directional derivative is the rate at which a function changes at a point in a specific direction, right? So sigma is a curvature parameter. So when you change sigma, you will get, see, different points like this. So the directional derivative is the rate at which a function changes at a given point in a specific direction. So you know that vector is always associated with the direction. So scalar quantity has just magnitude, and when it comes to vector it has a direction, and the directional derivative is the rate at which a function changes at a point in a specific direction. So since we have obtained a one-to-one connection between vectors and directional derivatives, then we can say that vectors can be defined as directional derivatives instead of direct line segments. So in a curved space or in a Riemannian space, we can say that vectors can be defined as directional derivative instead of direct line segments. Sorry. Vectors can be defined as directional derivatives in a curved space-time instead of direct line segments. Okay, so therefore in a curved space-time, x mu is not a vector. So you have to be very careful because in Minkowski space-time, in general, we write x mu as the 4 vector. But here in the curved space-time, x mu is not a vector. X mu actually defines a point. In a coordinate system, when you have x, y, z, etc., so you will define a point using the coordinates, right? The x-axis, some point, y-axis, some point, and some point from the z-axis, right? So, for example, point P is given by x, y, z. Similarly, here x mu is not a vector. What is a vector? Directional derivative is a vector. X mu just defines a point in the space-time. Okay, where mu can take 0, 1, 2, 3. So it will be x0, x1, x2, etc. So these are the points or the coordinates that define a point. Okay, so the vector associated with each point in a Riemannian space-time is directional derivative, and x mu is not a vector, x mu defines a point. Now, if that is the case, then just consider two different coordinate systems in 4 dimension. Okay, so in 4 dimension, just consider two different coordinate systems. First one, let it be x mu, where the coordinates are given by, it's a 4 dimension, so x naught, x1, x2, and x3. And another coordinate system, x prime mu. So this is a primed coordinate system. So here the coordinates are given by x prime 0, x prime 1, x prime 2, and x prime 3. Now these two coordinate systems are related to each other by a coordinate transformation, right? So they are related to each other by a coordinate transformation. And I will write that relation as x prime mu is a function of the unprimed coordinates x0, x1, x2, and x3. So the primed quantity is a function of unprimed quantity, right? Here you have to be very careful because this f mu, here also mu can take 0, 1, 2, and 3. So you will get the relation between primed and unprimed quantity, you will get 4 relations, f0, f1, f2, and f3. So these are 4 independent functions of the coordinate x mu. 4 independent functions of x mu. It has to be independent because this is a coordinate transformation rule from x mu to x prime mu. Therefore, these 4 function has to be independent. So how do you check whether the given relation is independent, linearly dependent or independent? So for that, you have to take, there is a necessary and sufficient condition for checking. So the necessary and sufficient condition for f mu to be independent of each other is that their Jacobian should not be 0, right? I hope all of you have learned this taking the determinant in mathematical physics. It's called the Jacobian. So here the Jacobian is given by partial derivative of x prime with respect to x, which is the determinant of the partial derivative of f0 with respect to x0, partial derivative of f1 with respect to x0, partial derivative of f2 with respect to x0, partial derivative of f3 with respect to x0. Similarly, you have to write up to partial derivative up to x3, and here up to partial derivative of f3. So this determinant is known as the Jacobian. And for these functions to be independent, this Jacobian should not be 0, not equal to 0. If it is equal to 0, it means that there is some kind of relationship between these functions, or these functions are dependent. In that case, the Jacobian will go to 0. Otherwise, the Jacobian should not be 0. So here the condition is that these functions, four independent functions of x mu, these functions are independent functions of x mu. Therefore, the Jacobian should not be 0. Okay. So written the Jacobian, the next step is to define the derivative. So I'll write the transformation once again. X prime mu is a function of f mu of x0, x1, x2 and x3. Now I have to write the inverse transformation also, right? So this is primed and this is unprimed. So here I have to write, in inverse case, I have to write x mu here in terms of the primed quantities. For that I use g mu. Okay, g mu of x prime 0, x prime 1, x prime 2 and x prime 3. Okay, so this is the inverse transformation. Once I have written this transformation and inverse transformation, now I want to find the derivative of x mu. So here I have x mu. Now I want to find the total derivative dx mu. So I have to take the derivative on the right hand side also. See here it is a function of four coordinates, x prime 0, x prime 1, x prime 2 and x prime 3. Therefore I have to take the derivative with respect to all the four coordinates and I have to sum it up, right? For example, dx mu is equal to partial derivative, total derivative of x mu is equal to partial derivative of x mu with respect to x prime mu dx prime 0 plus, now again partial derivative of x mu with respect to the next one is x1. So x prime 1 dx prime 1 plus partial derivative of x mu with respect to next one is with respect to x prime 2 dx prime 2 plus partial derivative of x mu with respect to x prime 3 dx prime 3, right? So you can see that when I take the total derivative of x mu, it is a very big expression. So I can actually write it in a short form. So how do I write it in a short form? So this transformation I can write as x mu going to x prime nu. So here you have mu and here you have nu. Okay, primed quantities I am representing by nu. Then the total derivative dx mu can be written as partial derivative of dx mu. Now with respect to what? I am writing x mu is going to x prime nu, right? So here partial derivative with respect to prime nu dx prime nu. So this is a very simple notation. Instead of writing all these terms, I can just write partial derivative of x mu with respect to x prime mu dx prime mu. And here see, you can see here there is a nu, here also there is a nu. So nu is repeating twice. So this is known as Einstein summation convention. So according to this convention, whenever an index appears twice in the same expression, it is automatically summed over all the other values. Okay, that is known as Einstein summation convention. Einstein summation convention. So according to this convention, whenever an index appears twice in the same expression, it is automatically summed over all the possible values. So here you can see, for example, 0 and 0, 1 and 1, 2 and 2, 3 and 3. So it is summed over all the possible values. Here I have taken 4 dimension, therefore 4 values, 0, 1, 2 and 3. So according to whatever you are considering, which dimension you are considering, that many summations will appear. So this is known as Einstein summation convention. And it's very simple and easy notation for writing big expressions. Right? Similarly, I can write the partial derivative of x prime, sorry, the total derivative of x prime mu as partial derivative of primed mu with respect to unprimed nu dx nu. Now this quantity we have already defined in the Jacobian. See, prime by dou x prime by dou x. So that will be dou f 0 by dou x 0. So there is here you have a matrix or a determinant, right? So similarly, I can write instead of this one dou f mu by dou x nu dx nu. Okay, just a notation. So these are all about tensors, sorry, vectors. How do you write vectors and what is the definition of vectors? Now slowly we'll move to tensors. What are tensors? So tensors are natural and logical generalization of vectors. So natural and logical generalization of vectors. So in scalars you had just magnitude, right? When it comes to vectors you have both magnitude and a direction. Now we are coming to tensors where you have magnitude, direction And the speciality is that this direction is specified on a plane. Okay, which means that tensor can have different orientations. So vector can have only a single direction, right? For example, vector can have only a single direction. But in case of tensors, it is defined, specified on a plane. Therefore, it can have different orientations. For example, first I will take Ohm's law. Okay, so Ohm's law in a linear isotropic system is given by J is equal to sigma E. Here, J is the current density, sigma is the conductivity, and E is the electric field. Here sigma, in a linear isotropic system, you have J equal to sigma E, and sigma is just a number. Alright. Now, when you consider an anisotropic medium, in an anisotropic medium, the same Ohm's law we have to write Jx, Jy, Jz is equal to, sigma is not a number here, it is sigma xx, sigma yx, sigma zx, sigma xy, sigma yy, sigma zy, sigma xz, sigma yz, sigma zz multiplied by ex, ey, ez. So sigma is not a single number in the anisotropic medium. It consists of a set of numbers. And here the conductivity is a tensor quantity. And see, it can have orientation, different orientation. It's not just a direction. Sigma x, 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 y, right? X, z, yx, yy. So these are all different orientations on a plane. So that is also possible, right? Now, second one is the moment of inertia. Now you have to consider a rectangular bar. Okay, consider a rectangular bar of mass m and length L. Mass m and length L. If I consider the axis which is perpendicular to the center of the bar, rectangular bar, okay, and I am rotating about an axis which is passing through the center of mass of the bar, then the moment of inertia I is given by ml square by 12, right? Now, same mass, same rectangular bar with mass m and length L. If I consider the axis at one of the edges like this and consider the rotation, now the moment of inertia of the same bar will be ml square by 2, right? So in the first case, if the axis is passing through the center of mass, then it is ml square by 12. If it is passing through one of its edges, then it is ml square by 2. So the same mass and same length, the moment of inertia changes with orientation, which means moment of inertia is a tensor quantity, right? Moment of inertia is a tensor quantity. Now, next one is very important. Whenever you go for a PhD interview or something, people usually ask this question: what is the difference between stress and pressure? Okay, what is the difference between stress and pressure? So, I'll just explain. Stress is a tensor, but pressure is a scalar quantity, right? I'll explain you how it is. Because stress, what is stress? So pressure, you know, it is force by area. So what is stress? So stress is also force by area, but it's not. But then where lies the difference? So just consider a surface, and I have an object on the surface. Okay, now I am going to apply a force F. So I will call this as F external. Okay, so once I apply an external force to deform this object, there will be an internal force that is there within the object, that will be coming from different direction, like this, like this. So these are all F internal. Okay, so whenever I apply an external force to deform an object, there will be an internal force. There will be some internal force within the object that will be in different direction. So stress is internal force by area. Okay, and this internal force, as you can see, has different directions. Therefore, this stress is a tensor quantity. Because this internal force is actually acting to reshape the object. So whenever I apply an external force, internal force try to make it back to the original shape, right? So that's why it is coming from different direction, and therefore stress is a tensor quantity, and it has a unit Newton per meter square. And pressure is the external force that I have applied, that has only one direction. I'm just applying in one direction. So this external force by area is a scalar quantity. And it also has the same unit, Newton per meter square. So in most of the interviews, they will ask what is the difference between stress and pressure. Stress is internal force by area, which is a tensor quantity, and pressure is external force by area, which is a scalar quantity. Okay. And one more example you can say, in the study of the motion of an electron in a crystalline solid. I think we speak about effective mass tensor of the electron, or the reciprocal mass tensor, right? That is 1 by m ij. So this is also an application of tensor. So this comes in the study of motion of an electron in a crystalline solid. So we speak about effective mass tensor, right? Effective mass tensor, or the reciprocal mass tensor. So you can also find much more applications of tensors. So these are the important applications of tensors. So from all these examples, we can see that tensor is a geometrical object that requires for its full description more than just one number, as in the case of a scalar, and even more than three numbers in the case of a vector. right? So mathematically, we can define tensors as arrays of numbers or functions that transform according to certain rules under a change of coordinate. So tensors are arrays of numbers or functions. It can be numbers or functions. Tensors are arrays of numbers or function that transform according to certain rules under a change of coordinate. Okay, so what is their importance in physics? In mathematically, they are just numbers or function. In physics, tensors characterize the properties of a physical system. So all these we have seen are the properties of a physical system: the stress, moment of inertia, conductivity, right? So in physics, they signify the properties of a physical system, right? Tensors characterize the properties of a physical system. So in physics, tensors characterize the properties of a physical system. Mathematically, tensors are just arrays of numbers or functions that transform according to certain rules under a change of coordinate. So that is the definition of tensors.